can't predict seismic events. We know they're going to happen. We know where they're going to happen. We don't know when. So they're playing a risky game at Diablo Canyon by.
Hi, you're listening to the Fairewinds Energy Education Podcast, hosted by the Fairewinds Crew. I'm Maggie Gunderson, and welcome to our show. Today we have Dr. Les Cannett, a special guest. He's on sabbatical with us this term from Johnson State, and he's a geology professor with 25 years of experience as a geologist. We also have members of Fairewinds Crew, Caroline Phillips, Program Administrator, and Arnie Gunderson, Fairewinds Chief Engineer. Today we want to specifically talk to you about seismic issues across the country and what that means for nuclear power plants. We also want to talk about the atomic reactors at Fukushima Daiichi and the seismic impact on them. What does it mean for a nuclear plant to face an earthquake? What happens? And what causes earthquakes? Can we predict them? Let's talk to our guest, Dr. Les Cannett, and let's talk to our Chief Engineer, Arnie Gunderson. Les, let's start with earthquakes. Weather management has come really far, and we get all these great predictions, and we see radar bringing weather in. What about predicting earthquakes? Can we do that?
With weather, we could see what's coming. With earthquakes, we can't. Of all the natural disasters, our worst predictions have to do with earthquakes. In fact, we cannot predict earthquakes at all. We have a number of stations throughout the world looking at all earthquake precursors in order to predict an earthquake, but we're unable to do that. There are changes in the strain in the rocks, which can be measured from satellites. Sometimes animals act unusually. Sometimes we think there might be some helium releases, certain gases from the ground. There are things called earthquake lights, known as brontides, strange lights in the sky or over marshes before earthquakes. Fantastic videos of these. But none are able to predict an earthquake. Out in California, for the last 15 years, there's been a lot of research going on in order to predict earthquakes, and still to this day, we're unable to do that.
I've read that California has one of the most advanced earthquake monitoring systems in the U.S. Now, I understand from what you've said that somehow that allowed them to give an early warning system, but that's definitely not possible.
Correct. There's no early warning system. Now, in Japan, what they have is some of their seismometers that are out in the ocean, when they detect an event, the travel times for the seismic energy to reach the country is on the order of seconds. So they have a few seconds of warning, but that's only after the event occurred. So in certain places, the seismometers have been set, they're linked to the trains and elevators in certain buildings where it shuts them down a couple seconds before the seismic energy reaches the towns. But that's not predicting, it's still after the fact.
Well, with that statement, let's talk to Arnie for a minute about Fukushima Daiichi. We've heard how bad the earthquake was out in the ocean, but that was not enough time to shut down the nuclear plant. Let's ask Arnie why.
Yeah, what happened is the earthquake was out over 100 miles offshore, and it was a Richter 9, which is, in my lifetime, I think there's only been about 4 or 5 Richter 9s, Nome, Alaska, in Indonesia, this one, and a couple others. When the Richter 9 earthquake hit out in the ocean, the seismic wave, like Les said, took a couple seconds to get to the plant. And when the plant started to shake, the power plant shut down. The control rods were shot into the nuclear core, and the chain reaction stopped. If that was all there was, the plant would have gone into a normal shutdown. The earthquake waves destroyed all the transmission towers, so the power plant had no other way of getting electricity except for turning on its emergency diesels. They worked for about half an hour and continued to cool the plant until the tsunami hit. And the tsunami was caused by the earthquake, but doesn't travel anywhere near as fast as an earthquake wave.
Question for you, Arnie. Do all nuclear power plants have that same switching ability that when they sense vibrations in the grounds, the control rods are automatically inserted?
What happened, for instance, down in Virginia at North Anna, when the earthquake happened, the nuclear core moved a little bit, and they detected the change in neutron population. In other words, there was too many neutrons on one side of the nuclear reactor and not enough on the other, and the nuclear reactor automatically shut down.
So that is true then for all. So in addition to a couple of rail systems in Japan and a couple of elevators in Japan, the only other thing that's set to shut down automatically from a seismic event might be nuclear power plant.
Well, a nuclear plant doesn't shut down. The difference is those trains get an early warning that the wave is coming. The nuclear plant didn't have that. When the wave hit, it shut down. But the trains have that couple of second delay. They know the wave is coming, so the brakes go on. And that doesn't happen at a nuclear plant.
Well, let's go back to the United States, to California. You just discussed what happened at Fukushima Daiichi. My question for Les is 9 is a huge number on the Richter scale. What sort of earthquake caliber are we looking at for a plant like Diablo Canyon?
The U.S. Geological Survey, over the years, creates seismic hazard maps for the entire country. Recently, they've been updated, and these hazard maps make suggestions as to the likelihood of a certain magnitude of event occurring at a certain location. The reason why it's not a prediction is we don't know when it's going to happen, but we know in a location the probability of an event of a certain size happening. So when the reevaluation of seismic hazards in the U.S. occurred maybe, a few years ago, in almost every case the hazards were worse than what we originally thought. And I believe for Diablo Canyon, yet Arnie could correct me, it used to be that they thought the event could be what is known as a 7.1 magnitude event, but now it's been upgraded to indicate that it's possible for a 7.5 magnitude event to occur in that location. So we often hear about Richter magnitude scales, and you hear 7.1 and 6.0, and it's kind of hard to get a handle on what that means, so let me explain it a little bit. Back in the 1930s, Richter came up with the Richter magnitude scale, and what he noticed was that if the ground moved 1 centimeter and was 100 kilometers away from where the earthquake occurred, that was called a magnitude 4 event. So that was the original scale. If you're 100 kilometers away from the epicenter and the ground moved 1 centimeter, that's a magnitude 4. If the ground moved 10 times that much, for example, 10 centimeters, that'd be a magnitude 5. And if it moved 100 centimeters, it would be a magnitude 6. So the ground motion increases by a factor of 10 for each increase in Richter magnitude. But the story is more involved than that, because it's more than just distance. Depending on the rock types, different rocks respond differently to the same amount of energy released. So we've converted what was originally the Richter scale into what is now called a moment magnitude scale. Yet when we report out to the press, we convert it back to numbers that people are familiar with. So a magnitude 4 might move the land 1 centimeter, and a magnitude 5 might move it 10 centimeters. But it takes 32 times the amount of energy as an increase from a magnitude 4 to a magnitude 5. So although the ground motion goes up by a factor of 10, the amount of energy released goes up by a factor of 32. So going back to Diablo Canyon, you hear 7.1 or 7.5, you think it's not that big of a deal because it's in the 10th place in the Richter scale. But recognizing that we're really talking about the amount of energy released, a magnitude 7.1 earthquake releases the equivalent of about 670,000 tons of TNT. 7.1 is 673,000 tons of TNT. Yet a 7.5 releases 2.7 million tons of TNT. It's about 4 times more energy is released in a 7.5 than we have a 7.1. You can think about it this way. If you get 25 miles to a gallon, because you get a certain amount of energy in a gallon of gasoline, you'd get 100 miles per gallon because you're getting 4 times the amount of energy out of that same event. So the question is the Diablo Canyon nuclear power plant really built to withstand 4 times more energy release than previously thought when it was constructed?
And to add to that, I know, Arnie, that operators at PG&E have claimed that they've upgraded the plant to withstand to 7.5. We have an audio to listen to what Gerald Strickland, the nuclear projects director at Diablo Canyon, and what he said on the issue.
Considering how robust the structures and facilities are constructed here at Diablo Canyon, in the event of a major earthquake, this is the place that I would want to be.
So, Arnie, is this accurate? Their claim that they have made the plant able to withstand a 7.5 earthquake?
You know, when you get in one of these nuclear power plants, they're so big, and a hubris sets in, and you feel like you're in control. And an engineer at Chernobyl, I think, really expressed it best. And here's his direct quote. We knew with certainty, with arrogant certainty, that we were in control of the power we were playing with. This was the day we learned we were wrong. And that same mentality affects the people at Pacific Gas and Electric in Diablo Canyon. And they did at Fukushima, too. You look at how big these buildings are, and you say, oh, this can withstand anything. But the reason they're big is because they have enormous forces inside them that have to be constrained. And when we realize that there's 4 or 5 million horses running around inside a nuclear core that's 12 feet by 12 feet by 12 feet, then you get an idea of why these plants are as robust as they are. Because the energy you're dealing with is so enormous that it's dangerous. So we all look at how rugged these buildings are, and it lulls you into a false security.
With that in mind, I'd like you and Les to talk about the New Madrid fault and what happened at the North Anna nuclear plant when there was a major earthquake there. So, Arnie, if you could just say what happened, and then Les can go in and talk about the fault and what all of that means. And there's a whole slew of earthquake zones on the East Coast as well as on the West Coast, and we never consider them as an issue.
Yeah, you know, living on the East Coast here in Vermont, you think that earthquakes are a California problem. But in fact, the earthquake near the North Anna nuclear power plant was an East Coast earthquake. And it also is known for damaging the Washington Monument. But what happened was that the ground moved underneath the power plant by about 4 inches. And you can see that because there's actually a picture of a fuel canister, and it's on concrete. And the concrete pad shows where it was and where it is. Now, the press reported that the canister moved 4 inches. But that's not what happened. You know, Newton's first law says that it's the earth moved under the canister, and the canister didn't move. So the earth moved 4 inches at North Anna.
Can you talk more about that, Les, and the earth moving that way and what that means?
When there's a seismic event, the land can move in a direction. It could move horizontally or it could move vertically. But the land also shakes, and the shaking could be from 15 seconds to a few minutes for very large earthquakes. And anything that sits on the ground when it's shaking might move. So the land itself might not move 4 inches, but maybe the fuel casks in shaking sort of slid across the surface of the storage pad. So for the event that you just referred to, I don't know how much the land moved in that area. But to have movements on the order of meters is common for very large earthquakes. And on the order of centimeters, it's certainly possible the land moved, but I don't know what happened there, what accounted for the movement of the casks in that area.
Well, there's a 4-inch mark next to the fuel canister showing something moved 4 inches, but that was a little earthquake in comparison to Fukushima, in comparison to what can happen at Diablo Canyon. At Fukushima, the entire seacoast dropped 3 feet. So sea level, whatever it used to be, things that were 3 feet above sea level are now at sea level. The entire coast of Japan sunk by 3 feet that earthquake. That's an absolutely incredible number, and it's likely at Diablo, too.
In the New Madrid area out in Tennessee, in that region, the land is moved on the order of several meters. That's a lot of movement from events. In the 1800s, there were 3 significant earthquakes in the New Madrid zone, 7.5 and December 16th, 1811, which is the one mostly reported. But that was followed by one in January 23rd of 1812 of a 7.3, and the following month of another 7.5 in that area. And those events are associated with subsidence, that is land moving down, on the order of 5 meters, yet the average is about 1.5 to 2 meters. So certainly the land can move horizontally or vertically quite significant amounts from seismic events on the order of 7s in this case.
You know, on top of that, there's a difference between the soil in the east and the soil in the west. When the earthquake hit at North Anna, Maggie felt it upstairs in our house in Vermont because the soil conditions were such that it can carry further. Whereas a West Coast quake, there seems to be more cracks in the soil and things don't travel as far.
You say soil, where maybe bedrock might be a better way to think about it. The seismic waves move deeper than the soil horizon. Different rocks have different strengths and therefore respond to the seismic energy differently. Here's an example of what I mean by the rocks responding differently to the same amount of energy released by a seismic event. So one of the earthquakes out in California devastated the Nimitz Freeway in California. It was this 2-layer freeway. And the freeway only collapsed where it was built over the muds. The amount of ground motion that was measured over the bedrock, or also known as ledge, was a lot less than that which was recorded over the muds. So the mud shook a lot more. And as we have seismometers on different rock types, we could see that the same event will result in a different amount of ground motion dependent upon not only the distance from the seismic event, but also the rocks on which the seismometer is mounted. So the collapse of that double-layer freeway only occurred over the muds. And the engineers in California knew that they were building that part of the freeway over rocks that were going to move a lot more than other parts. And it's an example of how much money do you want to put into a structure to protect it from what you perceive might be the worst case scenario. In this case, it wasn't enough.
You know what amazes? How many guesses there are along the way when you're designing for this. You know, first you got to guess at the magnitude of the earthquake, how much energy is coming out of the ground. Then you got to guess at where that is occurring. Is it, at one location or 10 miles away? Then you have to transmit that energy as a wave through the ground to get to the nuclear power plant. And then you've got to say, well, how does that affect the foundation of the plant? Then you've got to take all that energy up into the plant, and there's another series of factors called damping coefficients that affect how the building moves. And what Diablo Canyon did when their earthquake they determined it was much worse than what they originally thought it was, is they didn't change the plant. They just changed the numbers. They changed the damping coefficients. They just said, well, instead of a 2, we're going to make it a 6. And they just said, and it was an arbitrary change in damping coefficients. So to claim that the plant is any stronger is wrong. They just changed the numbers.
Right. So there are 2 issues here. One is different rocks transmit different amounts of energy. But it's also true that, from what you're saying, that the nuclear power companies reevaluate how strong their structures are to meet the codes, as opposed to rebuilding the plant itself.
And they're still doing it. This isn't when Diablo was built. It was designed in the 60s, and they started building it in the 70s, and then they realized they built it backward, literally. They built it backward because the drawings were the mirror image of what they should have been. And it was 1985 before it finally got done. But even now, they're still playing games with the seismic numbers. Diablo just had new steam generators installed. And rather than notify the NRC that the new steam generators really weren't as seismically qualified as the old ones, they installed them and then went back and change the numbers to make it work.
So it's a risky game they're playing. How many more years will Diablo Canyon be functioning, do you think?
Well, its 40-year license runs out in 2024.
And then they get a 20-year extension like all other nuclear power plants.
Well, they're applying for a 20-year extension, but there's really an awful lot of opposition in California. The seismic community in California, led by an NRC former inspector, Dr. Peck, have pecked holes in all of these calculations and shown that there's not a lot to support the conclusions that Diablo Canyon came to. So if they decide to ask for another 20 more years, I think it could be a real contentious hearing.
Again, we can't predict seismic events. We know they're going to happen. We know where they're going to happen. We don't know when. So they're playing a risky game at Diablo Canyon by changing their calculations to show their compliance with the new potential seismic events.
You know, it's sort of like being in Vermont and here, let's say it's winter's approaching. You know you're going to get a snowstorm sometime, but you don't know when and you don't know how much snow. Well, the same thing with an earthquake. You know there's going to be an earthquake out there sometime, but you don't know when and you don't know how much energy.
Right, and earthquakes are inevitable. I think about earthquakes the same way I think about hurricanes and volcanoes, in the sense when viewed through the lens of energy transfer. Earthquakes, volcanoes, and hurricanes, they're all rapid local releases of energy. And you could think about that as Earth's safety net. You can't keep building up all this energy. It's got to be released. So they're going to happen.
We've been discussing structures of nuclear power plants and how they're supposedly able to withstand enormous earthquakes. Let's listen to what Gerald Strickland, the nuclear projects director of Diablo Canyon, has to say about that.
Through our long-term seismic program, we've continued to learn additional knowledge on how earthquakes behave around the world, and we continue to apply those lessons learned.
You know, he's wrong in the data show he's wrong. There's a report on the Fairewinds website from a couple months ago that we wrote about the seismic issues at Diablo Canyon. If anybody wants to read it, it's about 40 pages. There's been 12 nuclear reactors that have had earthquakes happen under them in the last decade. The one here in Virginia, the worst one was Kashiwazaki Kariwa on the Sea of Japan. And then, of course, there was Daiichi. So there's 4 units at Daiichi that we have measurements from, 7 at Kashiwazaki Kariwa, which was the biggest nuclear complex in the world at the time, and North Anna. I guess you're 12 nuclear plants that have experienced an earthquake. In each of those, the earthquake forces on the buildings were higher than engineers expected. So the 1 in 10,000 year event has happened 12 times in the last 10 years. So what does that say about our ability to predict the really big one? The Kashiwazaki Kariwa was shut down for 4 years, and there was over 2,000 seismic restraints that were destroyed. North Anna had cracks, but no seismic constraints. And we do know there's a lot of structural damage as a result of the quake at Daiichi. So to claim that we know what the big one will really be, I think the last 12 power plants worth of earthquakes show we can't anticipate the big one.
We can't anticipate the big one, I agree. It is inevitable, but we take risks every day in our lives. And the question is, why do we take risks? Why do we take risks with nuclear power plants? Why do we take risks with building highways and hospitals in seismic zones? We want energy. People who are in the energy business want to make money. What would be an appropriate way for people to assess risk and still continue with their business as usual? So we take chances, and they're not always good ones because we have a short-sighted nature. We don't look far enough into the future.
One of the things we're seeing at a number of utilities and energy companies around the country is they're not assessing risk. They're padding the data considerably. And then now, as solar and wind are taking such a lead in our economy, certain utilities, for example, Florida Power and Light, Progress Energy in Florida also, and Pacific Gas and Electric are blocking their ratepayers, their clients, from getting solar or wind power. They're determined that they want to keep the nuclear power paradigm and have atomic reactors, which people can go on our website and see some of the data we've put up about the costs of doing that, and we'll also be releasing a study about that in the fall. The atomic power industry is refusing to let go of a technology that's outdated, that's extremely risky, as we can see from the horrible radiation releases around the world. On top of that, it's not cost effective. No one has a solution for the waste, and cost of managing nuclear power waste and decommissioning is prohibitive all around the world.
Maggie, you mentioned waste. Right now, Hanford has gotten a lot of attention with their nuclear waste leakage. It is located near the Cascadian subduction zone. I'd love it if Les would discuss the difference between subduction zones and faults and this additional risk to this already leaking nuclear waste problem.
Earthquakes occur along faults, most of the earthquakes. That means that when the rocks break, they release energy in the form of seismic waves, and we call that seismic energy. There are many types of faults, but most of the faults occur along what are known as plate boundaries. If you think of the Earth as an apple and take an X-Acto knife and inscribe 20 odd-shaped pieces on the apple skin, those 20 pieces would be the 20 major plates that represent the Earth. Take that apple skin and start moving it along the apple itself. Some of the pieces of apple skin will move apart. That type of fault is known as a divergent plate boundary. Some of the apple skin will move next to each other, side by side. For example, the San Andreas fault system. That's a transcurrent plate boundary. And some of the apple skin might move together, a compressional plate boundary, also known as a subduction zone. So in the case of the Cascade Mountain Range, which is in Washington and Oregon and Northern California, what we see out there is a series of volcanoes and earthquakes. The volcanoes and earthquakes in the Cascade Mountain Range are a result of type of fault where the two plates are coming together and one plate gets pushed beneath the other in what is called a subduction zone. So the Cascadia subduction zone is the name of a subduction zone in the western part of the U.S. What's happening out there is as the plate, the ocean plate just off the coast of the U.S., is being pushed under the North American plate, it moves in a stick-slip sort of fashion. So the stresses build up to the point where finally the rocks move, and that movement along a fault results in an earthquake. Subduction zone earthquakes generally produced the largest earthquakes. That was true in Japan recently with Fukushima, subduction zone earthquake. The question was related to what is a fault. Again, a fault is where one rock unit slides past another, and when it moves, that's the earthquake. In the Cascadia subduction zone, the lower part of the plate is moving at a more continuous rate, producing small earthquakes. But the upper part, which is more brittle because it's a lower temperature and under less pressure, is sticking. So we're concerned about large events in the Cascadia subduction zone because of this strain that's building up over the years. We've seen in the past couple hundred years examples of 7s, 8s, and 9 magnitude earthquakes out in the Pacific Northwest. And hence it got that name of the Cascadia subduction zone because of all the significant earthquakes and volcanoes along a plate boundary. Just as an aside, not all seashores are plate boundaries. The eastern seaboard of the United States is not a plate boundary. You have to go down to the mid-Atlantic Ocean. Just go on Google and zoom into the mid-Atlantic Ocean, and you'll see a ridge that separates the Atlantic Ocean as the plates are moving apart about the rate at which your fingernails grow. But the west coast of the United States happens to coincide with a plate boundary, and that's why the West Coast has continuous earthquakes and volcanoes, because it is a plate boundary.
The Columbia Generating Station is located even closer to the Cascadia subduction zone, and it is a Fukushima-like boiling water reactor as well.
Yeah, they claim that the Hanford site is America's Fukushima. And, I mean, it's already leaking and the ground is not shaking. So if a big one were to hit the Hanford Reservation, all those tanks out there would likely begin to release more radiation than was ever released at Fukushima. These tanks have bomb waste from a program that started in the 40s and 50s and 60s and 70s, and it's going to be another 100 years before we clean it up. So, one hopes that if the big one hits, those tanks maintain their integrity. And, if history is any indication, that's a false hope.
Well, I'd like to thank all of you for coming on today and doing this podcast. And I've jotted down many, many more questions. So I think that we'll definitely have to have you both back on, Les and Arnie, to talk about more seismic issues, how it impacts nuclear power plants, and 20-year license extensions. Appreciate what you've said. So to our listeners, send in your questions, and we will have these people back again and bring up this topic again, and we'll keep you informed.